Okay, so there are a couple of times, at least during this conference, IXPE was mentioned, so I decided at least I will tell you what it is. Yeah. So since I'm a member of IXPE collaboration, I was responsible for the group which is working on accreting neutron stars, so this is at least my obligation to do it. Okay, so basically, this is the first mission that actually can do X-ray polarimetry. There were missions like more than 40 years ago, also 8 called, that measured X-ray polarization from one source, Cygnus, two sources, Crab and Cygnus X1, and we were waiting for more than 40 years when the next mission could be realized, and this happened finally in the end of 2021 when the Imaging X-ray Polarimeter Explorer was launched. This is a collaboration between NASA and the Italian Space Agency. So what's different between this mission and whatever was proposed and actually flew 40 years ago is that the detection technique is based on photoelectric effect. So if you have a photon with polarized in the plane of the screen, that it will produce a photoelectron with a specific direction, basically along the polarization. There is some probability of that, proportional to the cosine square of the azimuthal angle. And then if you have a two-dimensional detector that actually trace the way this photon propagates in the detector, photoelectron propagates, then you make an image in the, so when the photon electron propagates, you sort of, it stays, they will get an image, and you measure the direction of the photoelectron, and then plot it as a function of azimuthal angle. Then from the amplitude of these variations, you can actually measure degree of polarization. In the laboratory, you can, of course, make all this, this modulation factor and relate to the polarization degree, and doing that to calibrate your instrument. And this is now, the IXPE is the polarimeter that has spurious polarization below 1%, much below. So it's actually, anything which is below 1% is clearly reliable. And during this talk, I will talk about X-ray pulsars and a little bit about QED effects that are relevant for the X-ray pulsars. So first, for those who are not working in astrophysics, okay, X-ray pulsars. These are not radio pulsars, of course, and these are accreting neutron stars. So we have a neutron star here, and most of these pulsars that I'm talking about, they have a large companion next to them, and there's accretion normally from the wind of the massive companion, and you have some focused wind, and you have some kind of accretion disk around the neutron star, but strong magnetic field disrupts the accretion flow, and then it channels the gas onto the magnetic poles. And basically, if you think about polarimetry, what this is useful for, you would like to know the geometry of the sources, right? So you like to know, but of course the problem is that polarization can be produced in many different places in this object. It could be in the place where actually matter hits the neutron star, the accretion shock or something, the accretion column. Most of the radiations come from there. Some radiation can be scattered from the accretion column as beam to the neutron star surface and reflected from there. And some radiation can be reflected from this accretion curtain, from the accretion disk, from the companion star, from the wind of the accretion disk. So many contributions possibly, and of course the tricky thing is distinguish between those. Okay, first we think that most of the radiation comes from the neutron star surface, and maybe it will be helpful. Okay, so before the launch of IXPE, we knew, like 40 years ago, actually there were models to predict what is X-ray polarization from the sources, and what is the beam pattern, how radiation is escaping from this accretion column. So if you have high accretion rate, you have radiation-dominated shock above the accretion disk, so the matter then settles down to the neutron star surface. This is called the accretion column. Radiation is escaping mostly sideways. It's called fan beam. For low accretion rate, radiation mass just falls on the neutron star surface, and then it stops at the neutron star surface. You have some kind of hot spot, but the radiation is beamed along the accretion, so it's a pencil beam. And then, depending on these conditions, you would expect different pulse profiles and maybe different polarization pattern. So basically, we would like to study all this using polarimetry. We wanted to actually, one of the things that we wanted to do with the polarimetry, to test what's called free precession model of Hercules X1. This is one of the X-ray pulsars that was claimed to have a precise neutron star, which means that it is not really spherically, spherical star, but there are some homogeneities. Anyway, or Donlai already mentioned that there is the effect that is most important for us is vacuum birefringence. And actually, this is not even vacuum birefringence. This is just a cross-section for Compson scattering in the magnetized plasma. It strongly depends on the polarization mode, and this is the X and O mode you see below the cyclotron resonance, and we are working. X-ray pulsars normally have cyclotron resonance at about 40 keV or so, and in IXPE range, which is between 2 and 8 keV, the difference in the opacities is about a factor of 100. So people were expecting that there will be huge polarization, just because in X mode you see hotter, you would assume that you see hotter you have lower opacity, as Don explained, and in O mode you see maybe cooler surface layers, and you will have less photons from the O mode. Okay, and we will see in the end that it's not true. Okay. Okay, then second QED effect is vacuum birefringence. When photons are born on the surface of the neutron star, they have to propagate to the observer, right? And here for us, it's actually interesting is this point source of the surface, basically a very small emission area, less than 1 square kilometer, much less. And the photons are propagating, and the polarization is adjusted to the local geometry of the magnetic field until what's called adiabatic radius or polarization conserving radius or limiting radius. And for X-ray pulsars, this is happening at about 20-30 radii of the neutron star. So basically, polarization degree, what you see, will depend on processes which operate on the surface, but polarization angle will be independent, basically, what's happening on the surface. Polarization angle will tell you what's the projection of the dipole large-scale magnetic field on the sky. Okay, so basically what we will be able to measure, we will be able to measure geometry of the dipole, because at 20-30 stellar radius, you would expect there will be no other contributions. Okay, so basically, if I manage to set it on, then this is, of course, movie not for the X-ray pulsars, but you can imagine there is a beam of X-rays, and you're observing, actually some of them are flying to you. So the rotation of this beam on the sky is actually telling you about the rotation of the polarization angle, if you look from the side. If you look from the top, then this polarization angle will make 2 rotations in one rotation with the neutron star. So it's because polarization angle is defined up to the 180 degrees, so we have twice 180-degree rotation. And this is what was expected, of course, and the models for that was proposed already for radio pulsars a long time ago, and for X-ray pulsars by Peter Mestarosh and colleagues already a long time ago. So basically, from the variation of polarization angle with the pulse phase, you can actually measure geometry. What you can measure inclination, which is pulsar inclination angle between the line of sight, this is O here, and the rotational axis of the pulsar. You can measure magnetic obliquity, which is the angle between the magnetic dipole and the same axis, right? And these are the main characteristics, right? And you can measure position angle of the pulsar axis on the sky, right? Which is here at cloud psi. So just from the shape of the polarization angle as goes with the pulsar phase. So this is done for like a dozen of pulsars. I'm not going to go details. This is what we observed. And just a couple of examples of the sources that I tried to show you the movie. So CEN-X3, Centaurus X3, this is the first X-ray pulsar that was discovered in the beginning of 1970s by Riccardo Giacconi. And there is some pulse profile that we don't really care. What's important that polarization degree doesn't really have very good correlation with the polarization, with the flux. Some high polarization degree at low fluxes, maybe you can explain this by, because you're not looking face on the spot where you have small polarization, but the flux is low when it's sort of, you look at the spot slightly sideways, okay, and their polarization is higher. Polarization angle does this more or less sinusoidal variations. I'm not going to discuss the some deviations, which basically tells you that this is the pulsar that you observe sideways, and there is just doing this way. And there is a swing by like 20 degrees. And it immediately tells you that the magnetic obliquity angle between the magnetic dipole and rotational axis is just about 15 or 20 degrees. Okay. Another pulsar, X per se, This is the closest to us pulsar at 800 parsecs, and it does this tooth-saw diagram. This is exactly when you look at from the top of the pulsar, and it rotates this axis that rotates below you, and so it does this twice rotation by 180 degrees in one period. And both of this data, both of these variations of PA with the phase can be fitted with the rotating vector model, where we just assume you have a dipole field and it does something, right? It rotates. So we can measure all these geometrical parameters for all these dozens of pulsars. What's interesting about this, of course, inclination of the pulsar to the line of sight is probably just a number that is, whatever it happened to be. You don't expect very small inclination because just from probability arguments. Yet, and as you see, there is high inclinations about 90 degrees. So here, of course, inclination can be between 0 and 180 degrees, actually, because you know whether you're looking for rotation counterclockwise or clockwise. Okay, so therefore this angle is defined with between 0 and 100 degrees, 180 degrees. On the other hand, this magnetic obliquity has some funny feature, which we found that some of the sources have very small obliquity, basically have dipole aligned with the rotational axis, and some of them are clearly have quite large obliquities, 90 degrees. We call them orthogonal rotators. And I'm not sure that there is any model that can explain easily this feature. Then, of course, one of the questions that arose immediately when we saw the first pulsar, Hercules X1, observed with IXPE, that polarization is actually rather low. Originally, we expected maybe 50, 70%, even 80% polarization. There were some claims for that. And we saw maybe 20% polarization, so it's clearly we'll be disappointed. Of course, disappointed just because when we proposed for the observations, we wanted to have very high quality data within 100 kiloseconds of observations, and with 100 kiloseconds we didn't get very good data because polarization turns out to be 4 times lower than expected. You need to have 16 times more photons to get similar quality data. Okay, so and then we try to understand what's happening. So we have a hot layer on the surface because you have particle actually hitting the surface. And then Donald already pointed out that if you have, we discussed with the question with Chris, that it's not standard atmosphere where we have like gray atmosphere for the star, you have hot matter inside and cold outside. It could be a much more isothermal layer, okay? And we made a toy model in this paper that we published in Science. Doroshenko is the first author. We just assume that you have a temperature is high outside some layer, and then there is transition to the rather cool underlying material. And then this transition happens at different column densities, like 0.33 and 30 grams per centimeter square. It's a toy model, okay? It's just, we don't know how deep this isothermal layer goes. I would guess somewhere up to here, maybe 10 grams per centimeter square, but this is just to understand what's happening. And then you do a radiation transport in 2 modes, and actually you do it in Stokes parameter, so you can allow for the transition between different modes at this vacuum resonance. That's important. In this layer, you can have vacuum resonance where we have one mode goes to another, and the result is that, for example, depending on the conditions where you are, for example, this black curve is for the 3 grams per centimeter square. Polarization is very low. This is average over flux, okay? And depending on the inclination, if you look at this, it can be X mode or this is O mode or X mode, depending on how you look at this. So it's actually becoming quite complicated. But the end result of this is that once you assume that you have isothermal layer and you have all these processes and conversions from one mode to another, you don't expect any more 80% polarization. You can have it anything you want, but maybe 20% is more reasonable. This is what you see. Okay, then I promise that with the data you can get sort of, maybe you can try to show that Hercules X1 is really freely precessing neutron star, or at least maybe, precessing neutron star. Right, and we have now 5 observations of the source in different states. These are called main on when this pulsar is bright, okay? and there is a shot on when it's weaker but still observable. So it has this 35-day superorbital period. So it goes 35-day period, sort of it changes the luminosity like that. Okay, the pulsars itself has just period about a second. Okay, and what we observed it in 3 times in this main on and 2 times in short on. And what we saw is that, okay, the polarization angle is the red one. Here you see clearly that this is average over the phase. You have 70 degrees in one phase and maybe 40 degrees in another phase. So it's clearly different. And what we try to do then, we try to fit this rotating vector model to the data at different states. And you clearly see that polarization angle as a function of phase has completely different behavior in 2 states. You fit the data and you get that inclination angle is very different between, let's say, 60 and 90 degrees. Magnetic obliquity is also varies between like 4 and maybe 16 degrees. So clearly it's an evidence, and this is very high significance, it's evidence that there is something going on there, the neutron star is precessing. The asphericity is at 10 to minus 7 level. So basically if you have 10 kilometer neutron star, 10 to 6 centimeters, this is just a millimeter, but it still is an observable quantity. Okay. One more thing that we learned from these pulsars that this has nothing to do with QED, but it's just interesting physics of accretion. Then we'll look at some bright sources, and there is one bright source with this long name. Actually, it has double names. And we observed it in 2 different, like we had 2 observations separated by 2 weeks. The polarization angle showed completely different behavior in 2 observations. You know, it was completely different. And when we fitted with rotating vector model, you have huge variations in all the parameters. And we thought this is a little bit too much. We don't understand what's happening, why it is such big variations. And then we looked at what's called Stokes parameter plane. This is basically how polarization varies with phase. And we saw that these objects, this same object tracks similar features, similar figures, but they are slightly rescaled, slightly different size, and the 0 point is in between. Okay, this cross there. And we start to think, so what's happening? And the only explanation that came to our mind is that this 0 point is basically wrong for this, in a sense. So there is some contribution of some constant polarization component that doesn't depend on the polarization, on the phase of the pulsar. So basically, if you are free to move the 0 point, let's say somewhat to the left, okay, then it means that all these points will be aligned and you will have exactly the same polarization angle. Okay, which is, in a sense, when we did this, it sort of become trivial. But basically, the assumption is that you have a constant component of polarization. So there is another source of polarization signal, not related to, to neutron star itself, the pulsar. On top of that, you will have a contribution from the rotating vector model from the pulsar. So you separate, and the Stokes parameters are additive. You will, in absolute sense, you will add them up. And actually, you can make a model where you have a constant source and variable source. And instead of having this extremely different polarization angle as a function of phase, you will get that the same model, same parameter for rotating vector model fits perfectly both data sets. Okay, but there is some contribution of another constant source of polarization. Okay, of course, and then we start thinking what it is, and the reasonable explanation is that it has nothing to do with neutron star. It has something to do with the probably accretion disk wind. So you have, in addition to the neutron star, you have some matter in the equatorial wind, in the accretion disk, and then you have a source in the center, and you have sort of elongated structure. Then you will have dominated contribution of scattering, Thomson scattering in the outside. So you will have the polarization along the axis dominated. And this easily can give you 30% polarization degree of the scattered component. If it gives maybe 10% contribution to the flux, it means that it's reasonable, but this is what you see. Okay, so basically, the conclusions are, at least for this part, that IXPE is now really opening the new field of X-ray polarimetry, and we are now able to measure geometry of many sources. I talked only about X-ray pulsars, but we have about 75 papers in the collaboration covering almost everything, accreting black holes of different masses, or supernova remnants, pulsar nebula, blazars, and, even gamma ray burst afterglows. And this is not what I wanted to talk about. Okay. And now for X-ray pulsars, actually, we can measure now directly geometry of the source. Of course, the precession of Hercules X1 is confirmed. Okay. And what's complication is that actually it seems that we have discovered that it's not only one source of polarization signal, but we have also another source, at least one more source, which is accretion disk wind, most likely. Okay, thank you very much.
Okay, thank you, Juri, for this very interesting talk. It's nice to see once again you add a new detector and you find lots of interesting things. I think that's true for everyone, isn't it? The talk is open for questions. I'm going to come to you first.
Okay, I'm not very familiar with pulsars generally, but when you're saying that you're going to use a toy model to predict the polarization, when you're saying that you are going to different layers in temperature, are you assuming some type of magnetic field to be constant in all of them?
Yes.
And also, when you see that you have a different prediction than like with the zero being more to the left, does that not get to like maybe a magnetic field configuration could be responsible for that? And also like accretion is from everywhere, not just for the pulse when you get it. So that should be everywhere, not just for the pulse.
Everywhere, you mean in the flux contribution?
Whatever like IXPE is actually observing, if it's not cooperating to the.
Okay, let me first ask the first question because I think it's easier. So you have a hot layer on the surface of the neutron star. We assume that magnetic field is vertical because this is where magnetic dipole sort of comes to the magnetic pole, so it's standard. It's constant. That doesn't vary across the region, just because it's a thin layer, okay, a few centimeters thickness on the surface of the neutron star. The size is also quite small. It's a fraction of a kilometer. So it's a constant magnetic field. Okay, so, under these conditions, you compute radiation transport. Of course, the model that we consider is a toy model, right? You have just some temperature inversion. Okay, in reality, what you would need to do, you need to do self-consistently how the particle bombardment goes through the atmosphere of the neutron star, how deep it goes, and, what are the processes that operate there, which is not, principle not so complicated probably, but not trivial either. Okay, and then, so this way we then predict what's polarization, degree as a function of angles. Then the accretion disk itself doesn't contribute to the flux. It's typically accretion disk is 100 cell radii away, so this very soft radiation. So it might contribute to the low energies, but not to the where you IXPE sees it. But it can, the accretion disk or the accretion disk wind can scatter some radiation, so there is a few % of flux that is just rescattered in the wind. Okay, so it's, I don't know whether I answered all the questions.
So, sorry, I missed about Hercules X1. Are you implying that the magnetic obliquity is changing at the period?
Because, yes, if you have a neutron star rotating, then it will...
the angle between the rotation and the magnetic axis?
Between their angular rotation, yeah. And
that's changing during precession?
I think so.
Why is it? Why can it change?
Now it's a good question.
Spin and the mu.
The angular moment. Okay,
why is it changing?
I think this could be happening that you have forced precession, right? If you have combination of free and...
Can you show the slides again? That you have a slide that theta. Just why is the inclination?
This is the Hercules X1.
Right. Yeah, this IP is the angle.
This is the angle between the rotational velocity and our line to sight.
Theta is
magnetic obliquity, right?
It's change. Why is change? Precession is supposed to change this thing. I don't understand it.
Okay, now I don't remember exactly. So you have let's say if you have a body, non-spherical, right? For simplicity, you just have Okay, so it's rotated not along the major axis of, of moment of inertia. Okay, so you can have.
It's usual classical.
It's yeah.
The magnetic axis is fixed in the body, right? So relative to the principle, but the spin axis is changing.
Spin axis. Probably Chris wanted to say something about this.
Well, can you constrain changes in the polar magnetic field due to the weight of the accreted material?
No, probably not. How you can do it? Yeah.
Well, if you're accreting for an extended period of time, that's a lot of weight.
I don't know. This is a tricky question.
Tricky questions can be taken off during lunch, I think. I see Alex, and then I come to the back there.
Thanks for the very nice talk. If I understand correctly, these fits are for the polarization only. Are you also fitting with, for example, light curve to get accretion? Okay.
Yeah. Okay, the short answer is that when you want to measure polarization, all these parameters, you fit only polarization angle, okay? So you can do it actually, what you can do, you fit Stokes parameters. There is some, let's say, some diagram like that, okay? So you can take the Stokes parameters with some error bars, okay? So the polarization angle doesn't have Gaussian distribution normally because it's a quantity that comes. If Stokes parameters are normally distributed, the polarization angle is not. So this you can account for, okay? Just taking not Gaussian distribution and what it should be. But then you fit actually just polarization angle. Okay, we don't have really the model for polarization degree, and there is no any model still for the flux. Okay, so if we would like to know that, okay, there is a tensile beam or a fan beam, but there is no really self-consistent model that will be, applicable and try to fit some really pulse profiles. People even, this is really surprising, but polarization angle is the simplest quantity that we can interpret.
Do you think this can help with modeling the pulse profile for either fan beam or?
I mean, if we believe the geometry that we determine, then of course you have much more constraints on your models, right? So you just take this geometry, and now you have to play with what's the centrals, or what's the accretion column or the accretion spot is doing, right? So basically, the flux that you see directly tells you what's the radiation that comes from the surface in a given direction. So we know more or less what's the compactness of the star. So basically, we know at what angle the photons are escaping from the surface. So at a given phase of the pulsar. So in the sense, you can reverse, right? We know the geometry, and you can go back and say, okay, this is what the observers see, this is what should happen at the surface. And then you try to make a model that fits that. But some of the objects are extremely messy, like VLX1 is it's a mess. It's a wind accreting, really, so there is no accretion disk there, so it's...
Okay, David, coming to you.
Okay, so hopefully these are easy questions because they're more on the detector side. I'm kind of curious about, a couple of things. One, roughly how many X-rays you need to sort of determine the polarization. And also, can you, I don't think you can, but maybe you'll correct me if I'm wrong. Can you tell the difference between being unpolarized or randomly polarized and circular polarization?
Okay. Okay, the second, so first the simplest question about the number of photons. I didn't have any formulas, but in principle, if you want to measure 1% polarization, you need 1 million photons. Okay, so there is some number, maybe factor of 2, I might be wrong, but it's about. So, there is the joke that if you have, there is a Chandra X-ray observatory, and which basically has very good angular resolution. You have 3 photons from the source, you have a detection. Okay, 3 photons is enough to have a source. Then you have, if you want to have a spectrum, understand this is a Plowell or black body, maybe you need 1,000 photons in some different energy bins. But polarization, 1 degree, you need thousands of times more photons just because you measure, the difference between 2 things at different inclinations. So that's a problem. Then in X-ray astronomy, we cannot measure circular polarization. In principle, it is doable in the laboratory. You need some magnets, some complicated equipment. In space, that's not feasible yet. So the only thing that we can do is measure linear polarization. it would be nice to have an instrument that can do circular polarization, but normally from the optical polarimetry, we know that normally it's 10 times lower than the linear. So my guess is that nobody will finance such a mission just to see tiny effects, and then you have then you need tens of millions of photons just to get anything out. So, of course, some of the objects will have probably quite high circular polarization. That's even X-ray pulsars might have them, but nobody will finance a mission just to observe X-ray pulsars, unfortunately.
Welcome to Dmitry and then to Andrei.
Thank you very much, Yuri. I understand there is lunch right soon, so I don't want to take up too much time. So I will make a comment rather than a question. So it doesn't require an answer right now, and it's a comment to all the speakers today. So far, this morning we heard several beautiful, very informative talks about radiation physics, about QED physics. But so far there has been no plasma physics, no collective phenomena. So an assignment, a home assignment for lunch, actually, for lunch discussion. I hope people will discuss how to connect all this exotic QED physics with collective plasma processes. Thank you.
Don't worry, there will be more plasmas as the sessions go on. Well pointed out. All right, final question, and then we will let people go.
So maybe suggest, so did I understand correctly, suggest for the fitting you use the dipolar magnetic field?
This is exactly, because
like so just if you have some deviation from a dipole, it could have in principle a profound effect on the polarization angle. So just I'm wondering, so just maybe you have thought about it, maybe this constant contribution for the polarization degree may come not from like the accretion disk or from the scatter, okay, so just from the scattering in the accretion disk corona, but maybe it is a result of deviation of the magnetic field from the dipole configuration.
Yeah, so in principle, we thought about this, but standard thing is assuming that at 20-30 stellar radius, you will have only dipole contribution. Okay, therefore, it's sort of, you have to invent something. Maybe it's misplayed the dipole. I don't know whether it will have any visual effects. Yeah. 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 So it's interesting if there is a good theoretical background to expect that there is, so one can think what is the observable feature of that. That could be, this is discussable, I guess.
Okay, I think we should close the session here, I'm afraid, so we have lunch. What I should have said was you add a new detector, you find a lot of interesting things, and then you get even more questions than you had before.
Exactly.
So on that note, can we thank Juri and the other speakers for the session today? And we start again at 2 o'clock about pair plasmas.